Hello, everybody. I know we didn't get to finish this lesson in class, so we will finish it right now. For those watching this in future years, hello. If it's 2025 and you're seeing this for the first time, welcome. We're going over measures of dispersion, and I'm going to minimize myself so that I can't see. I think you could still see me, but let's just work through this right now, okay? So, 2 classes, taking a quiz, and I know this is all written on because in class we did this already, but here are the means, the medians, the modes, and the mid-range, the summary data. And if you only looked at the summary data of these 2 classes taking a quiz, you might say these 2 classes are identical, Mr. Clody. Means of 71.5, medians of 72, modes of 77, identical in every way, shape, and form in terms of their measures of center. But if you look at the classes themselves, B is way more spread out than A. Okay? So measures of center tell you a story, but not the whole story. Today, we're going to talk about the measures of dispersion. First, and one of the most simple ways of finding a measure of dispersion or spread is finding the range, the maximum number minus the minimum number. And in class A, you've got 77 minus 65, so the range of class A is 12. For B, it's the 100 minus the 42, or 58. There you could see class B is way more spread out than A. Now, range is all fine. It's easy to calculate, but it's not going to take into account every score. Case in point, look at classes C and D. If I find the range of class C, everyone got a perfect score except for one kid who didn't study. The range there is 19. Class D is evenly distributed from a horrible score to a great score and a range of 16. Now, 19 and 16 are not identical, but they're similar. You might say these classes are spread out similarly, but they're not. Class C is clearly all the same except for one score. D is symmetrically spread out. So the range is fine, but it doesn't take into account every score. What are measures of dispersion that do take into account every score? The first that we'll talk about is called the variance. And there are, and I'm going to say more specifically, I didn't say this in class, these are called the definition formulas of variance. What are definition formulas? I'll put that in context versus another type of formula very soon. But there's a population variance and a sample variance. For population variance, we go Greek. We spoke about that. We go Greek. The Greek letter sigma squared. Okay, so sigma squared for population variance, S squared for sample variance. The formulas are similar, except you're subtracting mu from every score because that's the population mean, and you're dividing by capital N because that's the population size. For samples, you're subtracting every score by X bar because that's the sample mean, and you're dividing by lowercase n, which is the sample size, but minus 1. Why n minus 1? That represents degrees of freedom. Error gets reduced when you divide by n minus 1 with a sample versus n. All right, sample error gets reduced when dividing by n minus 1. Okay, we also did this in class. Calculating the variance by hand. You could put these numbers in by hand. There are 6 of them. That's why I wrote lowercase n equals 6. There's 6 numbers. The sample size is 6. First, you need to find the mean. Add up all the numbers. They add up to 42. Then divide by the 6 values, and you get a mean of 7. If I take everything and subtract by 7, 2 minus 7, I'll get negative 5. 3 minus 7, negative 4. 5 minus 7, negative 2, and so on and so forth. All right, and then I take all those numbers subtracted by the mean and square them, because that's what this numerator of the formula is. I'll get the sum of the scores minus the means squared, and that sum is 150. If I take that 150 and I divide by n minus 1, I get a variance of 30. Again, stuff we went over in class. Okay, you can do that by hand. My advice, put this into your calculator, these 6 numbers, and then do stat, calc, and then 1 bar stats. That's my advice for you on a calculator, that is. Okay, now I did want to specify that these formulas you see here are called definition formulas because there are other types of formulas, equivalent formulas, algebraically equivalent formulas called computational formulas. This was a set of 6 numbers, but we had to subtract each by the mean. That becomes a real pain when you have a set of, say, 600 numbers. I wish we wouldn't have to subtract every one of them by the mean. So there are equivalent computational formulas for everything. Okay? And the computational formula for variance looks, I'm going to say this straight up, it looks more complex, but in practice, it's much more basic. It is still S squared. That's the same. Okay? But the formula is this. It is lowercase n times the sum of x squared minus the sum of the x's, quantity squared, divided by n times n minus 1. I told you, that looks more complex. But look at the only things we're taking the sum of. We're taking the sum of the x's, and then we're taking the sum of the x squares. And notice what's not in the formula, x bar. So I'm going to do this right here. I'm going to use the computational formula. But the only thing I need in terms of columns are two columns, the x's and the x squared. 2, 3, 5, 6, 7, 9, and 17. I messed up there, I think. So didn't I? 2, 3, 5, 6, 9, 17. Yeah, this 7 shouldn't be there. I apologize. When I typed up this lesson, looks like I went a little bit too rapidly. It's the same set of data. 2, 3, 5, 6, 9, and 17. Okay, so if I square those numbers, I'll get 4, 9, 25, 36, 81, and 289. If I scroll down just a bit, the sum of my x's turns out to be a big number, 42. Well, small, but not big. The sum of my x squares is a larger number. It's 444. So now if I zoom out so you can see the formula, let's find the variance. Oops, scroll, let me make it just a little larger. There we go. The variance is going to be n, which is 6, times the sum of the x squared, which is 444, minus the sum of the x's, which is 42, quantity squared, divided by n, which is 6, times n minus 1, which is 5. I guarantee if you put that in your calculator, you're going to get a number. Guess what that number is? 30. Just for reference, what answer did we get for variance with the definition formula right above? 30. So you'll get 30 using either formula by hand. Most importantly, you'll get 30 if you take this, or if you take this data, plug it into L1 in your calculator, find the standard deviation on your calculator, and then square it. We spoke about standard deviation towards the end of class. All right, so there is the computational formula for variance. Now, just to talk about standard deviation is nothing more than the square root of variance. So instead of being sigma squared, it's just sigma for a population. Instead of being s squared, it's just s for a sample. So ladies and gentlemen, we are going to finish up this video lesson by talking about the variance for grouped data. And what I'm going to do is let me erase all this other hugabaloo right here that we wrote in class, because I want to have space to write, and I want to make sure that you fully understand what's going on here. So first and foremost, I am just going to list off the formulas for variance for grouped data. Grouped data means frequency table. So I'm going to give you the definition formulas. Definition formulas. Okay, so for a population, it's still sigma squared. Now this is going to look more complex, but it's not. It's the sum of the frequencies times the x minus v's, quantity squared, all divided by the sum of the frequencies. And for a sample, it's still s squared. Okay, let me do a little wavy line so you don't think that's division. It's going to be the sum of the frequencies times the x minus the x bars, quantity squared, divided by the sum of the frequencies minus 1. Looks familiar. They kind of look familiar, don't they? They look very familiar. Why? Because I'm just replacing n with the sum of frequency, basically. Don't worry, I will define what this means. So first and foremost, f, let me write it in red. F represents the frequency of each class. X. We talked about this before. With a set of group data, you need a representative for each class. So X represents the class midpoint or the class mark. So that's what I wrote here in red before. This represents the class mark. One thing I will do, though, in red, I'm going to write the computational formula. Again, this is going to look really complex. I'm only going to do it for sample variance, not population. All right, it is going to be the sum of the frequency. Remember, that's the equivalent of n, times the sum of the f times the x's squared, f times x squared, minus the sum of the f times the x's quantity squared, divided by sum of frequency times sum of frequency minus 1. I know this looks nasty. It looks nasty, but it's not. Replace all those sum of frequencies with little n's, and it's exactly the same as the formula that I wrote right here. If you take those n's and you replace them with sum of frequency instead, it is the same darn thing. All right, first and foremost, let me finish this up in the next 3 minutes here. All right, I'm going to take all my class marks and find them. So 62. And then I'm just going to add 5 to find the rest of them. 67, 72, 77, 82, 87, 92, and 97. I want you to take a good look at this formula right here, because this is the formula that I'm going to use to find my variance by hand. I need 3 sums. I need the sum of the frequencies, the sum of the f times x's, and the sum of the f times x squares. So sum of frequency, first off, is right here. The sum of the frequencies turns out to be 42. That's one of the sums that I need. Then if I just take f times x, 2 times 62 is 124. 1 times 67 is 67. 4 times 72 is 288. And I'm just going to do this. You can all do that. The sum of the f times the x's is a big number, 3,419. Okay? Then if I take this x's squared and then multiply by f, so 62 squared times 2, that's a big number, 7,688. 67 squared times 1 is 4,489. 72 squared times 4 is 20,736. Scroll down. The sum of the f times the x squares, that's a big number. It's 280,883. So to finish this up, let me use a different color pen. If I wanted to find the variance by hand, use this space right here. So s squared is going to be, use the formula, let me scroll up. Sum of the frequencies, so that's 42, times the sum of the f times x squares, that's the 280,883, minus the sum of the f times x's, which is 3,419, quantity squared, divided by sum of frequency, which is 42, times sum of frequency minus 1, which is 41. So if I do that, my variance is going to be 62.4. And if I take the square root of variance, I get standard deviation. If I do that, I'll get 7.902. Ladies and gentlemen, that's how you can calculate grouped variance of grouped data by hand. But as I showed you in class, you can use your calculator to get this information. If I put my class marks into L1 of my calculator, and I put my corresponding frequencies into L2 of my calculator, as such, I hit stat and enter, and like a good chef on a cooking show, I happen to have it prepared already. I put my class marks in L1, I put my frequencies, corresponding frequencies in L2, then I do stat, calc, 1 var stats, and I need to be careful here. My list of numbers is L1. My frequency list, I have to hit second, L2. My frequencies need to be in L2. If you have an old school calculator, you do one var stats, and then you have to hit second L1 comma second L2 if you have an old school calculator. And then I hit calculate. Take a look at the fourth thing down, SX. That's my standard deviation, 7.902. Let's look at our notes. What's S? 7.902. If I square it, I'll get the variance. Ladies and gentlemen, that is how you find variance and standard deviation using your calculator, and that's it. All right, have a great day, everybody. Bye.